Hello Year 12 and welcome to our 9th and final video here for series and sequences. We've been looking at the sum to end terms of GPs for the last two videos really, I suppose, something like that, the sum of GPs. And today we're going to look at recurring decimals, right, and their relationship to a geometric series. We have, as a bit of a teaser to the topic in class, looked at recurring decimals and how we might express them as a fraction. And we used a neat little bit of algebra where we might say x equals our recurring decimal and maybe 10 or 100x or 1000x or something like that. Right, and multiply our recurring decimals, subtract them, cancel out the digits and so on. That's all well and good. And that works perfectly fine. It's perfectly valid. However, we want to see if we can arrive at the same conclusion using our geometric series. Right, yeah. We're going to jump straight into an example so I can show you how this works. We're going to express these as a simple fraction. We're going to begin with 0.4 recurring. So that's 0.44444. Or if we express this as, right, as a series, 0.4 plus 0.04 plus 0.004, so on. We might recognize this as 0.4 plus 0.4 times 0.1 plus 0.4 times 0.1 squared, and so on like that, which looks a lot more like a GP now, where A equals 0.4 and my common ratio is 0.1. Right here. So now that I have a GP with a common ratio that is less than 1, we can do the sum, we can do the limiting sum of this. So the limiting sum, remember, is A over 1 minus R. So 0.4 over 1 minus 0.1. 0.4 on 0.9, multiply top and bottom by 10 to make it a simple fraction, we get 4/9. Okay, let's look at another example here. 0.0371. So this is 0.0371 plus 0.0000371 plus 0.70371 and so on. Expressed like this, where our first term is 0.0371 and each term is multiplied by a common ratio of 0.001 and as we increase. So we have a GP where my first term is 0.0371 and my common ratio is 0.001. Now the limiting sum, A over 1 minus R, is 0.0371 over 0.999. Multiply top and bottom by 1,000. Oh, sorry, by 10,000. And I get my head in the road. That's what I get. No, I get 371 on 9,990. I don't think that's going to simplify down. That's the end of the story. The good thing about doing these, they're fairly easy to check on your calculator. Just punch in 371 divided by 9,990 and hopefully you get the recurring decimal. Rightio, I've got one more to go here. This last one's a little more complicated again because I have a 2, right? 2.85 and the 85s are recurring. So what we do here is basically just cut that 2 off or separate that out. So I'm going to say this is 2 plus 0.85 recurring. So 2 plus 0.85 plus 0.0085 and so on, or 2 plus 0.85 plus 0.85 by 0.01 plus 0.85 by 0.01 squared, and so on. Now, this is a GP with A equals 0.5, R equals 0.01, and I have to add 2 onto it as well. Okay, but that's not part of the recursive part here. So my limiting sum is going to be 2 plus A over 1 minus R, which will be 2 plus 85. So it could be 2 and 85/99, or if you like, 283 on 99. I probably prefer the improper fraction, but you could go for the mixed number too. That'll be fine. Rightio. That's how we use the limiting sum of a GP to express a recurring decimal as a simple fraction. That's it. That is series and sequences. You know, if you've got any questions, make sure you ask in class. Maybe even jot them down before you get there so you don't forget. That's it. Rightio. I'll see you ready for the next topic, right, which is the fabulous mathematical induction. Okay. Thanks, 12s. See you then.